Hello everyone, welcome to today's Wolfram live stream. Today we have Nik Murzin doing some live science, live coding on his implementation of geometric algebra in Wolfram language. We also have Alexander.
uh, Basically took is first realize how to connect this geometric algebra to matrices, right? Well, first of all, I'm gonna tell you about how to install the Paclet and all that. Right? I just published it because it wasn't published 5 years ago because Paclet repository didn't exist yet. So now there's a whole definition as a resource and the published version of the Paclet in our opening there in our repository, right? So there's a page there's just published first time around a week ago, right? So I keep updating it and writing documentation. But basically the motivation me to write this Paclet 5 years ago was to make algebra nice before doing any geometry, because there are two parts to the geometric algebra. I actually like this nice quote by David Hastings that geometry without geometry is blind and geometry without algebra is dumb, right? So I wanted to solve the algebraic part for developing and implementing the geometric algebra. So I took this I found this nice book. This is the only book I have in print form for geometric algebra. It's Garrett Subjects Matrix Gateway to Geometric Algebra, right? So you can buy it or somewhere in the internet, I guess. So it was written around 1 year before I started writing it. So it basically describes how you can transform all the multivectors to matrices, and whatever you can do to matrices, you basically can do to multivectors. So I wanted to make it work for arbitrary algebra so that you can, without any complexities, basically transform back and forth between both. So right now it's just a special object. You can think of it as something that holds a lot of metadata for how you can describe coefficients for your multivectors, right? So you can customize it by giving it a signature, but more generally, there's a bunch of options that you can make it even more general. Usually, geometric algebra just described by these two indices, like how many basic vector special symbols here, but they are not properly documented, all of them are yet, right? So how this so if you have any questions at this point, please ask. Maybe you have a comment about how this basic structure works. Yeah, but again, I'm gonna show you how this matrix gateway works. So my original motivation is to implement this package in this sort of way, right? We're having this object. So I think I need to do this here. Right. So here's just by example. Well, you can see it already here. I have a comment that this whole gateway approach to multivectors is basically uses this simple identity that you can go from arbitrary geometric algebra with this two signature indices to the geometric algebra with one index lower in each of them, but basically storing them in the 2x2 matrix, right? You basically can package a bunch of the dimensionality into the matrix form, and you can apply it multiple times, given that you have some balanced number of indices when P, Q are almost equal to each other. You can basically decrease it until it hits the zero, so that you now have a large matrix with the 2 dimensions to some integer squared dimensions with just numbers, either G0, right? If you're going to apply this identity a couple of times to arbitrary balanced dimensional geometric algebra, you're going to get either G01 or 10, right? So it's either a complex number or a hyperbolic number. Actually, it's a good example to show. I have in this main page written a bunch of numbers, a little guide to representing different kind of numbers in the geometric algebra. So for example, from the simplest case possible, everybody knows about complex numbers, but you can also represent them by multivectors in this one-dimensional geometric algebra. And now you have a single vector that squares to -1, which we call our imaginary unit, right? So that's how we basically create this. You make a geometric algebra with this signature. You can format it as nicely as a complex number, and also format the last index as y, so that you can now when you create, so we can call this pseudoscalar I, right? And this is how you would create a complex number as a multivector. So you basically make an expression and you multiply by a pseudoscalar, some constant, add them up, and now you have a multivector. This is so it's a complex multivector representing a complex number. And now you have a bunch of different kind of tools available to you. You can apply like you can have like conjugates, which is like a complex conjugates, but this is like some kind of I don't even remember, some involution probably, some complements, some norms, traces, inverses. You can do squares, determinants. They all have like all these definitions, and they basically generalize to arbitrary geometric algebras, right? And they also generalizing some operations. So now you can have like exponentials, but you can even have arbitrary function. So you have a multivector function called on C, right? You can call it like, I don't know, some cosine, right? And it's going to apply it. Well, for the complex number, maybe it's not that exciting, but for some arbitrary ones, it's not trivial to do this arbitrary functionality, right? Applying arbitrary functions to your multivectors. And under the hood, it exactly uses this matrix gateway, right? Which I'm gonna, right? But before we go in there, there's also like I'm gonna show the hyperbolic number, because you only need to understand complex and hyperbolic numbers in order to understand how matrix gateway works under the hood. It's like there's like complex numbers is basically this minimal dimensional geometric algebra that has a basis element that squares to -1. Hyperbolic number is going to be the same minimal geometric algebra dimension 1, but with the additional basis element that squares to 1. So it has a signature 1, 0, or just 1. I guess you can do it like this, or this, right? So this is now the pseudoscalar in this algebra is going to square to 1. And you can, similar to the above case for complex numbers, you can now create hyperbolic numbers. And they all have going to define like similar unary operations and norms and whatever, right? And here, like a nice example, because hyperbolic numbers can be used for doing special relativity. You can, for example, for simple 1 + 1 dimensional spacetime, you can define what boost is. So by rotating your hyperbolic numbers by some given rapidity, and you can derive this in this way. For example, like Warren's transformation formulas for how velocity is being changed by boosting your frame of reference by some given rapidity angle, which is a hyperbolic angle. Well, yeah, by the way, here is an example of how geometric product looks like, right? And this one, I'm going to talk about where the symbol is coming from. It's a nice when we're going to talk about geometry. So, and you can enter it by GP. So there's a nice shortcuts when the Paclet is installed and loaded. There's some nice geometric Paclet shortcuts are created, so we can create geometric products like this, and also anti-geometric products. That's why that's where this notation is coming from, right? That it's like a combination of a dot and a wedge, because the geometric product in some sense combines those two binary operations together. But okay, so here's just a small example of how we can multivectors get transformed to matrices using this fundamental identity, basically. Right? This is just a random example, like given like two random multivectors from two different geometric algebras, three-dimensional ones, right? You can first, there's a function that creates a matrix from the multivector. It's formats it, and it's not like a built-in matrix. It uses this multivector array, which is more general way than just storing it as just a list of lists, or also columns or whatever arbitrary vector, because it also there's a shape there that also by default it basically kind of iterates between two negative and positive dimensions. So it's basically shows you that it's has the covariant and contravariant indices as a different way of basically the shape is not the same as dimension. So the negative dimension shows you that the dimension is covariant, not the contravariant. So it's just a nice way to store the multivectors and work with the tables of multivectors. So that's the matrix, right? And there's a nice functionality to just go from one geometric algebra to another, just converting multivectors of the same dimensionality. It basically works as follows, because there's a nice way to incorporate a built-in imaginary unit from the Wolfram language, which is just for creating complex numbers. You can basically convert every geometric algebra, because by default you assume that all the coefficients are real, right? All the geometric algebras usually come with real coefficients. So you can basically use complex numbers functionality to transform nicely from one signature to another by just multiplying your corresponding coefficients and treat them as though you change the actual basis element, right? So that's basically how you can, for example, switch from 3-0 signature to 2-1 signature by just multiplying some of the vectors by imaginary unit, right? So that now you basically assume that it's now squares. I think this is incorrect, but actually, I think it should be like this. Otherwise, not it. Whatever. It should be one of them just squares to -1, right? If in this algebra all of them squared to -1, here one of them has to square to -1. So you have to multiply only this one by I. This one is incorrect. Now because it's anyway, I'm gonna edit it. Hold on, so that I don't forget. Maybe I just go for this version. It's like a development version. Okay. No, it's too big. Where was that? Written. Oh, here. Go away. Anyway, so after you convert it, you have these things. You can convert back and forth. You can see that there's imaginary units appear in the coefficients, even though I've started from arbitrary random real numbers. So that's how the conversion works. You can go back and forth. So that's you can confirm it, and also you can convert from matrix to multivector backwards. So this identity also holds. You can convert multivector to matrix, and also notice that the matrix contains in these two different algebras that we started from. The matrix contains coefficients as multivectors, but in different algebras. So we apply this identity, right? That's why we chose different signatures for our example algebras, 3-0 and 2-1. Is that when you apply this identity, you're gonna end up in a different basis number. It's gonna be either complex or hyperbolic. So for example, for this V multivector, which is the element of this geometric algebra 3, right? It's gonna contain complex numbers as its elements when you convert it to matrix. But this W multivector as an element of geometric algebra 2-1, it's gonna contain a hyperbolic number as its basis element when you convert it to a matrix, right? So essentially, this gateway works as soon as you know how to work with complex matrices and hyperbolic matrices. You know how to work with arbitrary multivectors. So that's the premise, right? So I just need to implement arbitrary functionality that can apply functions like determinants, squares, exponentials, and all that to matrices of complex numbers and hyperbolic numbers. That's why I basically implemented as this multivector array, because there's no built-in hyperbolic numbers in Wolfram language. There are complex ones. There are complex numbers, so I could have basically kind of assumed that this E-1 with underbar, this represents a pseudoscalar in this G01 geometric algebra, but we don't want to lose this information, because we're going to mix our coefficients that contain the actual complex numbers and this one. So we kind of have to represent it as a minimal multivector in this minimal geometric algebra. So that's why the multivector array as an array of multivectors is useful. Okay, so it's like a design decision. And yeah, so and under the hood, when you convert this matrix either multivector to either matrix with a complex or hyperbolic numbers, you can apply some matrix functions to them. You have to like be careful with hyperbolic numbers. You have to do some algebraic manipulations in order to be able to treat to do some manipulations of hyperbolic matrices. But you can actually, there's some nice properties that you can actually use complex numbers instead of hyperbolic ones in order to simulate the behavior. So that's how it works under the hood, right? For example, like this is just confirming that the back and forth conversions work, right? And here it's like the gist of how it works under the hood. It's like under the hood, if you have some imaginary, like some pseudoscalar or some imaginary unit that squares to -1, you can represent arbitrary matrices, like a complex matrix can be represented as this, right? And when you exponentiate it, you can make take a sum and a difference between those components and exponentiate them separately, so that basically this identity holds. But in this case, when you do the complex numbers, it's kind of you don't have to do it, because when you multiply it out, basically B is gonna just cancel each other out. That's why I think I say it right here. B's are gonna cancel it out, and you could as well just exponentiate your original sum directly. But with hyperbolic numbers, you can do the similar trick, and this is actually matters, because if you had some unit now that is not one that squares to one, right? So you can actually represent it by this y. And when you do the same trick, when you don't use this one and you exponentiate your sum and difference separately of your like real and imaginary components, basically matrices, you can do the same trick, but now this one does not multiply it and there's nothing to cancel. So now you can basically, that's how the exponentiation of hyperbolic matrices work, right? So that's how you can do some arbitrary operations on multivectors that get reduced to some array of hyperbolic numbers, right? And here is basically one example, and that's why it works. And now when this gateway is working, you can apply anything. Like for example, you can apply inverses, right? This is just a multivector function which goes through this gateway when it converts to your multivectors to matrices and back. You can apply some arbitrary functions to them, like inverses, exponentials, logarithms, and so on. So for example, you don't have to do some manual pen and paper work in order to figure out what is the inverse of the vector or bivector or arbitrary rotor or motor or whatever. You can just do this gateway and apply just a general procedure for arbitrary multivector, right? So now you can inverse everything that is not singular at the end of the day. Yeah, so this is just confirming that everything works when you do the logarithm arbitrary. This remember, we started with arbitrary vectors, right, with some numbers, right? Yeah, and this is like multi-vector block is like one step in between this procedure, because you can apply it. Multi-vector matrix goes all the way to the hyperbolic complex numbers, but you can apply it once, right? If you apply it once, you basically have a block of higher order higher order multivectors, right? If you apply it twice, you recover the multivector matrix. So that's why you can blockwise reduce the multivector to the higher and higher dimensional matrices. Yeah. So and that's the whole setup. So that the whole mechanism under this Paclet. That's how the most algebraic part of all the functionality is, how is it implemented under the hood. So yeah, so that's the algebraic part that I had to figure out 5 years ago when I started writing it. But there wasn't too much geometry. Well, if you have any question about the algebraic part, now I want to talk about some geometry, because we're still blind without it. Even though we made it a little bit less dumber by going for all this gateway and make it as general as possible. Yeah. All right. So the geometric part is kind of still it's still not complete. I'm still in the process of going through it, right? So I know Alejandra was talking about conformal geometry, but it's a little bit more complicated. So there's like a projected geometry, which is like one dimension less and doesn't work with like spheres and circles and all that, with all round objects. So I started with this one. This is like more developed currently. But as a resource, I started with this nice work by Eric Lengel. He's like done a great job actually making a good resource, which wasn't available like 5 years ago. So it's like he wrote a book called Projective Geometry Algebra Eliminated, which has this nice pictures and very tight, like very neat implementation, we can say, and development of all the geometric algebra operations for this, both projective and conformal cases. So, and that's kind of what I took as a resource to go through to implement all of the operations properly. And that sign for geometric product that I showed is basically that's where it came from. So this kind of resource use it as is basically an official sponsor of those symbols, as it says here, right? But this is like you can see that there's like a bunch of operations. I like this poster. Basically, what I'm doing is going through the book. I have the book here somewhere. I'm just going page by page, almost like maybe going back and forth and just implementing all of it into the Paclet, starting from this projective geometry. I already implemented a little bit of conformal one, but basically all of these operations neatly organized. And there's some nice concepts that does not exist in other books and other resources for geometric algebra. So, so this is like I think it's the best one. Is the best source for learning it, and also the concepts that it introduces is also the most nicely packaged together. I know, right? So there's like some concepts that do not exist as far as I know, do not exist in the other projected geometry and conformal geometry implementations, right? Like what are the bulk, but they're more geometric in nature. And what I have currently, yeah, this is the PDF. I'm working on this note, just like just tries to package up all the examples and some nice geometric scenes. I'm just going about this book and screenshotting some of the like tables most of the time, like yeah, and trying to implement it using this Paclet. Anyway, so the most simple geometric case you can do is the flat projected geometry, right? Which is just goes from this special context in this Paclet. There's all the projective geometry functions implemented in the special context. So all the basis vectors, they're also reordered in some special way, renamed so that it also basically corresponds to one-to-one corresponds to all the definitions in the book. So that's why I generalized the geometric algebra so much, so that it supports arbitrary basis and arbitrary ordering and formatting, so that they can just implement and make it look as much as possible, as close as possible to the book implementations and how it renders their formulas and identities. So for example, like I want to go through all of the book and kind of do some like maybe dynamic or just static nice visualizations like this for all the geometric operations that you can do. Like this is, for example, like the basic joints, meets, and like projections. Like in 2 dimensions, there's not too much you can do. Basically, given a point, like first of all, there are a bunch of useful functions that you can use. For example, there's PGA points. Hold on, did they? Yeah. So if you have an arbitrary 3D point or 2D point, right? It's going to work. This is like converts to a multivector in 2D if you're given a point in 2 dimensions. That I did it so that you can basically just start making graphics, right? Because you have a graphics and you make a point, or you just basically, if you have a geometric object as a primitive in Wolfram language, you have to have some functionality for convenience to go back and forth between them. So given some geometric objects like a point, line, plane, circle, or sphere, you just given as a primitive of Wolfram language, would be nice to have it some functionality to go back and forth between multi-vector representation and the actual primitive that you can just put in your graphics functions and render it immediately. So that's basically what this kind of functions do. There's like this is like very general ones. For example, if you given a region and you want to convert it PGA, it's gonna figure out what this region is. That's for example here. For example, let's check how this is implemented. Oh, yeah. So, for example, a random point here, just a like some point and another point. You can do it like this, right? So if you wedge it together, you get some multi-vector, but then, for example, you don't know what you don't know anything about projective geometry, and you want to just figure out what kind of primitives can be encoded in this multi-vector. You can just ask what are PGA regions contained in there. It's gonna return all like an associations with some of the objects that potentially can be encoded in there. Like there's maybe some vector. Well, this is a zero vector, so very nice. Not very nice. Like, but this also contains a line, so you can just extract the line from here, and now it's just a primitive that can be sticked into the graphics and rendered. So if you have this point, and you can basically show that it indeed corresponds to some plane going for this line, right? Like this, right? So that's why you can go from back and forth between regions and multivectors. And that's what this example shows you. You can use directly what, if you know that it's a line, you can use a line. This is like the actual wedge, and also some projection, I believe. Yeah, this is some PGA expansion. I think it's projecting, which is basically projects a point R on a line L, and line L is just this wedge between these 2 points. So that's how you can basically work and make geometric scenes using this Paclet.
That's really slick and a good implementation of the symbolic nature of Wolfram language. So is that using up values?
Yes. Well,
also,
if it
you
can,
have like you give it the line.
Well, it doesn't have to use up values. It doesn't have to use up values. You just convert back and forth between them. So you can usually, like PGA point is basically can go back and forth, right? So multivector, if you apply it once, it can try to extract the point back, right? It knows what projective geometric algebra it's using all the code, so that it can be either 2-dimensional, 3-dimensional, maybe in general any dimension.
I see.
But here it doesn't have to use up values. It's just the definitions. So you can have to convert them back and forth depending whether you want to stick it into the graphics, or you evoke it with a multivector. But maybe that's actually a good point. Maybe I have to. You can define some nice sub values that work directly on the points. Like for example, maybe I want to define, like, if I had a wedge product, which I don't, I just have a up value for the wedge, which knows how to, for example, wedge 2 points together like this, right? But maybe if I can define a wedge product and define how it works on the points directly, if it's convenient. So like, right?
They make your own
So it
function
knows how to convert. Yeah.
And
especially when you maybe
as a comment on the projected point, it adds a third component for the E3. Like PGA point.
Yeah.
Right. Okay.
Like here it's that's the origin, right? So this multivector 2-dimensional projective multivector E3 corresponds to the origin. right? And there's some like PGA origin function, I believe.
And what's signature on E3?
Wait a minute, on the PGA itself, on the algebra or what?
In the algebra, yeah, E3 has what signature? To make it projective.
Well, just 210 for the two-dimensional case, right? And for PGA, which is three-dimensional, this is 310, so we can extract it like this, right? So this is like a 2D case, this is a 3D case. And if you want to make it conformal, you add one more and make it 4-1. I have a CGA, or it lives in a different, yeah, it's gonna be 4-1, I think. But still kind of, I think I have it here. Now it has a CGA and this signature is 40, yeah, 410. So it's a bit different. So that's the convention of the book I'm following. I think it's a little bit varies from offer to offer. I think that's where this PGA eliminated book is the convention what it uses. Well, maybe not the signature itself, but operations definitely. Yeah, but again, like this up value definition, maybe what this kind of anti-products and geometric products, because those are some of the operations that are the most used, I believe. You can overload it to work like this, which doesn't work yet, but as a default case, when you have a geometric primitive, like a point, line, spheres, and so on, you can make it this thing to work, which could be nice, because I want the functionality to be as simple as possible to use. Right, yeah. All right. So, so that's 2D case. It's not very complicated because there's just points and lines. There's no planes. Right? There's like a single plane. But for the 3D case, it becomes more interesting. So you add one dimension. Here's just some basic identities and multiplication tables for how to do join and meets, right? And how they modify the dimensions of your multivectors. This is just simple examples for. This is the same creation of the line as we did for the 2D case, plane. They all just join and meets under the hood, right? So you create it like this: you random point, random line. This is just primitives that you can immediately plug into your geometric scene, right? So this is a point and this is a line, right? So this is like when you turn it into a multivector like this, using either PGA line or PGA region. I think it it's like a region PGA. It also works, right? So if you don't want to specify to think about what kind of conversion you're doing, you can just do this. Right? This is the general. It knows what the primitive is, and then you can project back. Yeah, but you also don't know which regions this multivector contains. You can again do the backwards PGA regions things. It again gonna extract all possible regions that can be contained in the multivector, maybe checking some of the constraints and all that. Right. Yeah, and then you can plot them. And so basically that's the basis for working with geometry. You go back and forth between primitives and multivectors. And there's more and more examples like this.
So multivectors
like there's a
can be interpreted as like a weighted sum of these regions.
Well, they're not really weighted, but yeah, they can be. The same multivector can contain multiple of shapes in its coefficients, like a point and a line, and but it's a little bit tricky because they can mix together. And because I still haven't finished like go through the book, I don't understand it yet completely, right? I still have to refresh all of the geometric part for all of these operations. Like all of this, I'm just like literally I wrote it like these examples I wrote yesterday, right? Just going and through the book and defining, like making these definitions, like what those definitions are doing, and making some example scenes, Like this is line through point. Given a point and a plane, find an orthogonal line. Uses this expansion function, which is just implemented using a wedge product again, right? The outer product and some dual of another multivector. Yeah. Projections. There are like at least four different projections outlined in this book, right? This is like, for example, blue objects are being projected to red objects. So here I think it's like you're given a point, a line, and a plane, and you project point to a line, right? So it's like orthogonal. This line is projected to a plane, and this point is projected to a plane. So you have three different projections you can do. So it's an ortho projection. There's also an anti-projection, which is like something similar but backwards. Like here again, blue goes projected to a red one, right? So it's so you're given two plane, again a plane, a line, and a point, and when you project one thing to another, I guess like this is a line projected to a
That's like
point,
moving the
which basically
plane
got shifted.
to that point, and then the shortest, like a parallel translation.
Yeah, just parallel yeah, just basically parallel translation. If you project a line to a point, it just gets shifted. If you do it to a plane, it also gets shifted. What's this plane? Given a G, so we have anti-projection, so a line to a point, plane to a point. Oh yeah, this is like this blue plane is got projected to a point, right? And this line is got, well, it's a bit weird. I don't remember what to do. I think cyan, I figure out that cyan works better. It's like it's also nicer because it's like a negative colors, opposite colors. So in a way, nicer to show those relationships. This is even more complicated types of projections that go through the origin. This is also me trying to define all these different projections and line. This is just showing this. I'm not gonna go through all of those. Yeah, another yeah. The transformations I still haven't finished all of them. There's some simple ones like reflections. You can reflect a vector, which is again given you can construct the plane or bivector corresponding to some of the vectors that I'm not even showing here. Well, there's a plane, I guess. Yeah, I'm showing there's a plane. So you're reflecting a vector over into the, how do you say it even? Yeah, you're reflecting a vector in a plane. And this is the geometric algebra sandwich product that you do it like this. And I believe I also implemented some because you don't have to remember this kind of things. I think I started implementing things like plane reflection, right? So that's how you can define it. So this is the sandwich product. So it actually have looks better when you use the anti-geometric product. Don't have to inverse it. But this is like the vector reflection, I guess, have to work with bivector. But when you actually given a plane, like I think I have the example here. Yeah, that's the definition I want to show. Right. So if you actually have given a plane so that you can convert it as into the multivector, then you can use this anti-geometric product in order to reflect any shape in that plane. So you don't have to think about bivectors, and you don't even use the inverse and things like that. Yeah, translations. Yeah, and I haven't even gone through this one. So this is like still on my to-do list. So that basically a motor is like a rotation plus translation. There's some things like flexors, who knows what. Yeah, and then there's like you can combine a bunch of them together. This is the hero image for the Paclet that I'm trying to make here, but it should have a much prettier example later. And I guess what is left to show is the conformal geometry case, which I haven't done too much of. It's not even working correctly in most of the cases. I have it made working this sphere example, just like intersecting the sphere. So it's basically the same design as the projective geometry, which I think actually have to be combined together so that you don't have like a conformal and projective case, like different things, because all of the definitions have to work across them. So in a way, I don't have to make like this region CGA separate from the region PGA definition, so that it has to figure out, it can figure out what is the geometric algebra is there under the hood and what object we're using, right? So it can make it much simpler. But here's like a simple example, like when you just use the meet operation to find the intersection for two spheres, and it also finds the intersection like a imaginary intersection, right? So if your spheres do not intersect, you actually get the complex coordinates when you perform this operation. And if you ignore the complex coordinates and take the real parts, you basically get recover this particular circle. So yeah. But yeah, that's on my to-do to make all the conformal and round cases also documented in these tech notes for the Paclet. But I guess that's all I wanted to show. Maybe there's more, but I maybe have some questions. I can, while you think of question, I maybe figure out what else to show. What else do I have? All right. Yeah. I have some spinners, which is basically from we have algebra, we have geometry. We just need some physics also implemented. So there's some nice space-time algebras, not that have some Lorentz factors, and you can represent Pauli algebra, Dirac algebras, and given this matrix gateway, there's also some nice correspondence between Pauli and Dirac matrices, because you can go between from multivectors to matrices, which are like so that your spinners actually look like column vectors in matrix representations. So this is like a very ugly multi-vector representation. When we use a nice basis for your matrix, you can make it look like you usually represent spinners as your column, as your four-dimensional columns and all that. Yeah. So there's much more physics to be done. Maybe some non-relativistic examples by just like applying geometric algebras. You usually apply linear algebra to your physical problems, like doing some moment of inertia computation or whatever. This kind of examples. Yeah, there's a different kind of numbers you can do. I haven't shown the dual numbers, but this is like when you create a lot like, yeah, well, I actually showed it, but yeah, this is like a third type of number, you can say, that has a element that squares to 0. But you can mimic it by just having two other vectors. It's just a convenience in a way. It's like saving you one dimension. That's by the way how it works under the hood when you have this dual signatures. And when you want to convert it to a matrix and backwards, it actually cheats a little bit because I haven't figured out how to do it properly. It converts it to, like, if you have this signature, it converts it to this signature, right? It just strips it out, but adds one for positive and negative signatures together, so that you can basically construct a null vector out of this two, something like that, right? And I know how to build my complex and hyperbolic matrices out of these signatures, so something like that. Yeah. What else? Yeah, this is broken examples. Sorry, still debugging. Yeah, the conformal geometric case is also interesting because it's in this book. It also uses some non-standard vector basis or not non-standard metric. So instead of so that's where I had to specify the custom basis for my geometric algebra. So it's not identity. So it's basically in some custom way mixes one of the basis elements. So that's how you can represent this geometric algebra from the book without and still support all of the complex hyperbolic matrix gateway applications. Basically, if you know the metric, if you know this metric, you can kind of diagonalize it, make your matrix gateway, and then undiagonalize it back. So that's how it's currently working. So yeah, so it still works even when your metrics are not as simple and not diagonal.
Can you elaborate what this vector basis is representing?
This is basically what you multiply on your, like, for example, you can extract, not like this. If you extract your vectors, right? That's the how many what your dimension is. That's how many vectors there are in your algebra. And this is basically the matrix that you have to multiply in order to construct some new vectors, right? So that's basically your some linear map. Well, this is actually the inverse of it. I actually don't remember. So basically, the geometric algebra contains a signature, right? As I told you, that encodes a diagonal metric, right? So it looks
here
like
this
this.
is saying that E5 squares to -1.
Ask it again. E5 squares to.
Yeah, in this signature,
Well, if
the square of E5 is -1.
I copied it weirdly. Yeah, it actually
Okay,
squares to
so
0 because.
So the second
So
coordinate in that signature 410 that corresponds to null vectors.
Yeah, I think the proper way to actually do it, it's not like this. It's first of all you have a pure geometric algebra which is diagonal, which just this with the same signature like this. Wait, what? Yeah, so you have if you have a geometric algebra without any vector braces specification, you just have a diagonal metric, right? So you have like this. So this signature just purely corresponds to what are the squares of your basis elements are on the diagonal, right? So that's why there are 4 ones and single -1. So that's a diagonal metric for the default signature geometric algebras. If you want some custom metric, you basically specify what your basis transformation, right? And you, I think it's like by default it's like this, and then you call it this is going to be E4 in this new conformal geometric algebra, and this is going to be called E5, right? Something like that. So you perform your basis transformation.
So it's actually still the same algebra, but it's just a different basis that you've chosen, right?
Yeah, but it affects how everything is formatted.
Yeah.
And
Now you
formatted.
use for your last 2 vectors in the algebra, instead of having a positive and a negative signature, you have a null signatures.
Yeah. So this is like that's how the metric looks like. And this is like one of the things I had to figure out like recently because this metric custom metric support I just done like this last week, and I have to figure out how to actually generalize all these geometric products and all the operations to arbitrary metrics. And I thought that the metric should be, because that's how in the book it is written, that it seems like the metric is the main actor, right? You specify the metric as your dot products between basis elements, right? That's how you customize your geometric algebra. But actually, it's not very convenient because given a metric, it's not clear how to use arbitrary metric to derive your geometric product. I haven't I found a very complicated formula I coded it up, it didn't work properly, right? So like given an arbitrary metric, how you can actually, how to write a geometric product. It's not very trivial, but I just realize it if you forget about the metric, but just customize the vector basis, because you still have to do it usually in practice. And then from the given basis metric matrix, you can just derive the metric. So it's in a way your metric emerges from that. But given the vector transformation, it's much easier to perform geometric product. You just convert back and forth, right? So in a way, it's much simpler to think of in terms of basis transformations than arbitrary metrics.
Right. So if you have like a positive signature vector and a negative signature vector, then like the diagonal, there's a null vector in between somewhere, right?
Yeah, but like in this conformal case, like these two vectors are null vectors, right? So
right, but if you had signature like one positive, one negative, then there's a vector combination in there that is null. Is that true?
Right. Yeah. If one positive and one negative, then their sum and their difference will each give you a null vector.
Mm-hmm.
And you can use those as your new basis.
And so that comes up like, for instance, modeling Minkowski space. You have positive and negative mixed signature, and then you have null vectors on the diagonal, on the light cone.
Yeah, right.
Yeah. Just trying to figure out. Yeah, I think you have to use the inverse in this case. So that's one should be null, right? So that's how it's constructed. So that's the E4 and E5 in this definition of conformal algebra out of this diagonal one. So this is the null vectors. One is like corresponds to some origin and some infinity or something like that. Yeah.
Comments from chat. We have
and because of this,
Rotten Piranha is asking about rolling on surfaces and magnetic fields or charges on rolling surfaces. I don't know if any of that applies here.
No, I don't. Well, as I said, I don't have like a lot of geometric examples done yet, and how those. But yeah, if you have like this kind of physical, mechanical applications, I think it's going to be done later. Like I'm going to go through these geometric implementations of all these geometric algebras first, maybe generalize them as much as possible, and then do some physics examples, like mechanical maybe scenes, and some different kind of computations. Yeah, including rolling on surfaces done with geometric algebras. Yeah, I think that's about it.
So Nick, I do have one question. For constructing sort of arbitrary functions on the geometric algebra, typically something like an exponential is formally defined as a power series. I mean, because in the geometric algebra, you basically have the products. And so for arbitrary functions, you need to define them in terms of just multiplication. And so a power series is a common way, but of course, a power series is not a closed form. And if you're trying to make it give a sort of closed form expression for some general function, then it sort of gets a little bit more specific into terms of the signature and things like that. You have to tailor it. Do you have some general way of creating these functions, or how do you do that for general functions?
Well, that's the thing, because you know how to do it in closed form for matrices, right? I can just leverage whatever computations Wolfram language is doing for matrices. Like I given some symbolic matrix like A, B, C, D, and I want to exponentiate it, right? It does something, right?
Yeah. Okay.
So the same thing for the multivectors. Like given some multivector, maybe in two-dimensional algebra, that's what's gonna do if you try to exponentiate it, right? So it's gonna exponentiate some kind of matrix and then transform it back. So it works for symbolic cases, so for arbitrary multivectors.
Okay. Yeah, that's neat.
And because of the symbolic nature, I think some nice functionality that kind of would work for very dynamical scenes that there's a lot of geometric manipulations happening, because it's very difficult to actually perform them like many times a second. It's easier to just go compute just symbolic case once, right, as a formula.
Right,
It
yeah.
works as some kind of JIT compiler, just-in-time compiler. You compile the symbolic function that went through this matrix gateway back and forth to derive your formula, and then you can just use it to draw your scenes, right, dynamically, more efficiently. Yeah. So go ahead, install the Paclet, use it, complain when something doesn't work. Yeah, it's gonna be better. Slowly.
Okay, well, this is great.
That's incredible. Very good work,
Thanks,
Nick. Yeah, we
Okay.
look
It's
forward
very
to
cool. I love how you take it to the whole new level.
Sorry, what?
Very excited that you said. I love how you take it to a whole new level.
Trying to, yeah. There's too many geometric algebra Paclets. There's just has to be one done right. Perhaps I'm just trying. Actually, Alejandro, what is your Paclet is called? Can I find it? It's like
It is CGAlgebra. But
Just
every time that I try to look at it, doesn't appear. I think it's because it's really recent. CG with the instead of the P.
I can hear it. Hold on, can you? Algebra
CGAlgebra.
PG. Why is it not?
CG, sorry. With that C of
Doesn't work. Okay. Do you have a link? If you have some good examples there that I can salvage and make it work for my Paclet, would be nice. It's like the more examples of applying these things, the better.
All right, so Alejandra, what signatures did you work with? Oh, thank you for the link.
I said
CG algebra.
sorry again. Can you
Uh-huh.
repeat?
What signatures did you work with when you made your Paclet?
For this one, you can set the signature that you want, but yeah, it is. You can set it up. There is. Oh, I actually don't know if we documented that part.
Like the fact that there's no built-in circle 3D kind of bums me out a lot.
Yeah,
Yeah, there has
it
to
is.
be.
Exactly.
Yeah.
Yeah, but then I'm excited to start playing with your Paclet. I will try some of the examples that I already have. See if it will be cool.
Yeah. There's still a lot that if you're interested in conformal geometry, I think this last chapter is basically it's very cool. There's still a bunch of concepts that I don't understand though there. It's like I still don't understand what's the difference between flat points and round points because I haven't read it. I've seen some pictures. It's like but there's some difference between them. I don't know. So, but as I think if Eric claims that it is the most natural representation of conformal algebra, I can't believe him. So there's like two kind of flattened objects, flattened or round objects. There's some kind of dipole. I already implemented some. I think it's like going to be shown as a tube in 3D. This is going to be dipoles. Default primitive for representing dipoles. So it's not just circles and spheres. There's some other kind of shapes that are naturally represented. There's some weird.
As a
concepts
dipole,
like
2 points that are inverted about the origin?
Oh, there's
Or can it be
there are 2
anywhere?
points, but there's some kind of radius.
Mhm.
There's some kind of radius also given, so it's a bit like a flat tube. That's why you can think of it as a tube
Oh, I see.
in 3D. Though it's like I think it's shown is like this. Just it's almost like a inverse circle in some way. So basically the same information as a circle, but it's different.
Hmm.
Yeah, there's a lot to learn. So still going through it, implementing functions. lot to do there.
Oh, definitely a lot to explore for next steps.
Yep.
Well, all right. Thank you, Nick, and thank you to Richard and Alejandra for coming along and giving your opinions on it. Thanks everyone for tuning in to the live stream.
I look forward to downloading it and playing with that.
You can do it right now. I just uploaded it to the Paclet just before this talk. The latest version is there. You can install it now.
Okay, I'll be sure to post that link to the video description on YouTube.